Hey, welcome everybody to Coffee with Caleffi. Delighted to have Tommy Olsen on board today. He's going to do a cogen presentation, and I'm a nerd about this stuff. I've been a motorhead all my life, from the mini bike and go-kart days up until current. And as you know, I'm a hydronics nerd too. So this is a product that really plays into both of my weaknesses, Tommy. So I think you're going to enjoy this. They've got some good data on units that are operating out there, and I think it's a unique opportunity for a lot of the folks that are tuned in today. So we'll do a couple housekeeping slides here on the front end, Tommy, and we'll get going. Yeah, so on the top there, that's just some information about if you have problems connecting or have bad audio or something like that. You know, sometimes just dial in again and try it over, or that's a tech support line for the GoToMeeting people at the top there. At the end, after the presentation's over, you'll get a little survey, and if you want a copy of the PowerPoint of this, or probably be a PDF file that we'll send it out to you, you can check a box there and we'll make sure that you get that. And like all of our Coffee with Caleffis, it'll be archived on our YouTube channel. There's tons of YouTube videos there. So if you want to go by our YouTube channel, and you can see stuff from all over the world that we have on our channel there. So it gives you the opportunity to view it again, or if you have people in your office that couldn't make it today, they'll be able to see it here. Probably about a week, we'll have it up there. So that's that. And we do send this electronically. We'll mail out this certificate of attendance. You know, it might be able to use that for continuing ed credits or something like that. It's we don't have this certified by anybody, so you know, most of the time your licensing bureaus will accept a certificate like this to give you some hours for your plumbing license or engineering license. So we'll be glad to send that off to you. Okay. And then, yeah, next month this is a hot topic right now. In fact, Tommy and I were talking about this a little bit before we started. So Siggy's going to be back. Our Hydronics 27 will be on this topic also. So he'll, you know, whenever we have a new Hydronics out in July, Siggy kind of goes through with a presentation. So put that on your schedule. Okay, I think we're getting close to, and you know, I met Tommy at the HR show. I don't know him real well, but we had a great little chat there. I think we've got a lot in common as far as our nerdiness in this type of product. So I think you're going to enjoy his presentation style and certainly his knowledge of the product. So it's all yours, Tommy.
All right, well, good afternoon, everybody. And I want to thank Caleffi for inviting me to speak on a Coffee at Caleffi presentation. Today we're going to talk about cogeneration, in particular micro-cogeneration in relation to domestic hot water. So today's topics I'm going to bring to you is, you know, what is cogeneration, some reasons why cogeneration in this category, the different types of cogeneration that are out there, some basic components. We'll go through some typical installations, and then we'll talk about marketing opportunity and where you can get other resources regarding micro-cogen opportunity and information. So to start off with, you know, what is cogeneration? What is micro-CHP? Well, cogeneration is simply the ability to produce heat and power from a single fuel source. In this case, it's either natural gas or LP, and the terminology for micro, it's more of a street term. Typically, when we talk about micro, we're talking about systems that are under 50 kW, okay? And the CHP, of course, is combined heat and power. So what we're referring to today are systems that are under 50 kW. These are not big self-sustaining systems. These are not critical infrastructure. This is the opportunity to provide cogeneration to a whole nother customer base. So why cogeneration? Well, first off is energy efficiency. I mean, we're producing electricity on site, so we don't have the production losses, nor do we have the transmission losses that you would normally see from a power company. In addition, we are recouping the heat from the engine, the generator, and the exhaust system to use to put into domestic hot water. Now, how does that stack up against power companies and the power plants? Well, with micro-cogeneration, as you can see on the left, we're utilizing 93% of the heat that's produced. So we're using it either for electricity or we're using it for heat. Compared to basic power plants, we're bringing a lot more efficiency to a customer in their building. So the utilization of both heat of all the power, all the BTU capability of the natural gas input, we're able to extract out in two sources. Again, heat and electricity.
Tommy, let me break in for 1 second. I forgot to introduce that Eric is on board with us from Lochinvar too. So if anybody has a question, I can see some of them typing in there. If you're, he's going to answer some of those as we roll, and we will leave time at the end to answer questions. I know Tommy's got a nice rhythm here, so I don't want to keep interrupting him as he rolls, but we will have time at the end to do live questions, and also Eric will type in answers as we roll here. So,
yeah, okay. So moving forward, the other question is why cogeneration is environmental. Okay, so micro-cogeneration is a very clean burning process. It's very low emissions. As an example, the Lochinvar product that I'm going to use an example today, our XRGI 25 that is produced by EC Power out of Denmark, we have passed the first level of CARB certification for California. We're in the process of now going through our catalytic converter lifetime test. That is where we have to run the engine to get the exhaust through the catalytic converter for a set number of hours. It's constantly evaluated. So it's just the longevity of the catalytic converter, but the emissions itself, we have met CARB certification standards for a standalone micro-cogeneration system. Now, keep in mind too, there's a lot of things out there with power plants. You got fossil fuel plants that we're trying to get rid of, but they emit large quantities of CO2. We've got nuclear power plants that you got to do something with spent fuel rods. But natural gas micro-cogeneration with stoichiometric combustion, again, it really does well to reduce greenhouse gases. That is big on a lot of our customers' mind right now. We're seeing a lot of state and business self-imposed mandates to reduce carbon footprint. Many of our customers are using micro-cogeneration now to help achieve those goals. Give you a quick example. We had a project up in upstate New York at Finger Lakes Community College. They have a green initiative, their board of directors, their state advisory board, and everybody, they have a green initiative where they wanted to reduce their greenhouse gases, but they wanted to use some new technology. So they were in the process of updating their domestic hot water system with a couple of Lochinvar wall-hung boilers and some hot water generators that we produce. And so they wanted to add the cogeneration system with it. We worked with them and our rep and ESCO up there to get this installed. Interesting fact, they use this system. They fill up the hot water tanks for their domestic hot water. When they reach that capacity, they can divert the system over to their hydronic system. And we installed this in the summertime, and last winter they gave me a call, and it was interesting. One of the issues that they had for years that they didn't know how to resolve was that after about 10 o'clock at night when classes were over, the night setback would kick onto their main boilers for their hydronic system. It would come on again about 5 in the morning, and they would get a lot of condensation on their interior windows in the classrooms, and it was doing damage to the sills and so forth. What they decided to do overnight is to just divert the 163,000 BTUs into their heating loop, just put this light heat throughout the building. And what wound up happening unintentionally was that they were able to eliminate their condensate issues on the interior windows. Now, the 24 kW easily absorbed because they had parking lot lights, they had hallway lights, they had different areas where they had lights maintained at night. So there was use for the power, so they had no issues with absorbing 24 kW. So again, the environmental benefit is a big issue with micro-cogeneration. Another one is an ROI. People want a return on their investment. Typically, we look to have an ROI of 4 years or less, and that's a combination of your natural gas cost versus your KW cost, as well as any incentives. But in addition to that, there's the hidden cost on commercial bills, and that's called the demand charge. And in many cases, this can be up to 50% of a facility's power bill. And what happens is, if you're not familiar with this, is that the power company will take and they'll monitor your electricity usage every 15 minutes. And what happens is, when it spikes at a peak, that is your demand charge peak. And so they look at what you normally use and everything in between there. And that bill can go, instead of paying 10, 12, 15 cents a kW for your regular kW usage, it could be upwards of 7, 10, or even as high as $15 a kW for going into your peak demand area. For example, our facility in Tennessee, we checked our facility out, and sure enough, I mean, we were about 40% of our bill was demand charge, but we looked back and it made sense, because every morning we're turning on laser cutters, plasma cutters, a lot of high power equipment that's making a big inflush draw of power first thing in the morning. Once everything up and running, the system the amount of power consumed drops down. This happens on a regular basis, even on small scale. And I'm going to show you an example of that. We've had a project up in Canada where we did a farm application where we put in 6 systems for their main building, and then we did a single unit in their hog barn. If you're not familiar with a hog barn, you need a lot of hydronic heat, because the piglets have to stay warm even in the summer. There's also a lot of electricity use, because if you've been around a hog barn, you need some big fans to ventilate the area due to the odor. This was off our customers' tracking data as far as their power consumption before we installed the cogen system. As you can see, their base consistent load every day in that hog barn was 10 kW. Essentially, though, based on the spikes in demand, they were basically using 20 kW. And then there's this one day in this profile that was at 30 kW. Well, their peak demand charge was everything above 10 to 30 kW. So their bill was extremely high, not because of their kW rate, but because of their peak demand charge. When we installed the cogen system and put the 25 kW into the system and utilizing 163,000 BTUs of heat, as you can see, we brought their power consumption down to below their regular usage of 10 kW. Okay, this went a long way in developing the ROI on this facility, because it's a 24/7 operation. So when you're looking at these projects, it's not always about the base rate of kW cost versus natural gas cost. It is the demand charge, and in many cases, it's not spelled out as a demand charge. It's called different things in different parts of the country. Different providers, they hide it throughout the bill, and most people just pay their bills thinking, gee, my facility bill is $8,000 a month, I got to pay this. Not understanding that that could be 30 to 40 to 50% of that bill could be related to demand charges. And I'll show you some other examples later as to how we help reduce demand charge in some other buildings. So briefly, we're going to go through just some different types of cogeneration out there, to provide information as to what's out there. And then like I said, again, I'm using Lochinvar product as an example, and I'll show you what we have. So we talk about prime movers. That's what's generating the power and the electricity and the heat. And so you have Stirling engines. The Stirling engines, they do well in producing a lot of heat, but they don't produce much electricity by comparison. It's very low electrical output. The other thing out there is micro turbines. These systems tend to make a lot of electricity really well. They are not all that much on heat generation. In addition to that, on micro turbines, you have to keep in mind that their efficiencies are affected by the atmospheric conditions in which they're installed. And lastly, there's internal combustion engines, and that's what we use in our product is an internal combustion engine. It generates the best heat to power ratio of the three. It produces a good amount of heat, in our case, 163,000 BTUs and 24 kW electricity. The engine that we're using is a Toyota 4Y natural gas engine. Okay, you heard me right, this is a Toyota engine. This engine has been built since like 1985 and is more commonly found in every lift truck you've ever seen at a warehouse throughout the country. Okay, being that it is a Toyota engine and everything involved with it, the maintenance on this is extremely simple. Now, if you're familiar with large-scale cogeneration, you're familiar with the fact that you have to take a week to 10 days sometimes to do full teardown maintenance of an engine. In this case, when it comes to micro-cogeneration, most of the systems out there, including ours, need minimal maintenance. In our case, it's simply an oil change, air filter, air filter, spark plugs, a couple of sensors, and some maintenance hoses that have to be changed out that can be done in a matter of 2 to 3 hours. Very simple process, about every 4,000 to 6,000 hours. Takes you a little time overnight to let the engine cool down. So your main downtime is roughly between 10 to 12 hours every 6 months, if in fact you're running this 24/7. In a typical applications that we have installed, we're experiencing basically one maintenance cycle a year, based on basically a 4,000 to 6,000 hour runtime, running on 16 to 18 hours a day minimum on a project. So again, we don't want to tear this engine apart. Additionally, the longevity of this engine, if you have a Toyota, you know good and well those engines will run several 100,000 miles. In this case, these engines are designed to operate upwards of 60,000 hours without mechanical overhaul. In terms of an 18-hour day, that becomes 10 years. We've seen products like this in Europe. I've been there to see actual installations of this product that's been installed since 2005. They have engines approaching 80,000 hours that look like they just came out of the crate. So very reliable and a very strong running engine with minimal maintenance. So the generator types, there's two types of generators. There's synchronous generators, which have backup power, and they require extensive capacitors, battery backups, and disconnect procedures to avoid backfeeding the system into the grid in the event of a power outage. Power companies do not want to endanger their line workers. The other type of generator is an induction generator. That's what's found on the Lochinvar system. It's an induction generator. It basically, we're supplemental power. If you think about it, 24 kW is not going to run a building. What we're offering is supplemental power because you need that base load of thermally led heat for your domestic hot water. Okay, it requires the grid to operate. If the grid goes down, we go down. Power companies really like this feature because there is no chance of backfeeding during a power outage. At the same time, if the facility already has a backup generator, say it's a hotel and they already have a backup generator, it will read that generator as a grid, sync with it, and then essentially throttle back that generator, the 24 kW or however many units we have hooked up, and reduce the wear on the generator. So again, for a micro system, you're looking at supplemental power as your best investment. Again, because you don't want to depend 100% for 100% of your power. We want to do this thermally led and get the byproduct of electricity. We'll talk a little bit about the base components. It's common to basically all micro cogens. We have the prime mover, which is the engine and generator. There's a heat exchanger. Sometimes it's mounted within the system. In our case, it's mounted external to it. There's a control system. Again, can be mounted within a unit or out of a unit, depending on the manufacturer. And there's a stratification storage tank. Okay. Now, the stratification storage tank is necessary because, being that it is an internal combustion engine, we have to maintain a certain amount of cooler water going back to the engine to, one, keep the engine cool, and two, have something to reheat to provide into the heat exchanger. The tanks are designed to stratify. There are 4 sensors located on the units. You can see here the 4 sensors and a control box that communicates back to the control panel. And what it's looking at that stratification layer. So if we see a stratification layer get down below the 4th sensor, it says I have enough hot water, that's as much as I can take, and it would turn the system off. On the other hand, if we were reading all the hot water at the highest level at sensor 1, it may click on a backup heater, and we can talk about that when I go through some diagrams in a couple of slides as to how to design these systems. And then, I'll let Bob talk a little bit about, what Caleffi components are available that work with it, that coordinates with this product.
Yeah, thanks for the turnover. So yeah, we wanted to play in the game here a little bit. So we obviously there's a hydronic component to this, or there could be, in addition to the domestic water application. So everything that we make for hydronic systems could certainly be used in this system. So I think we've got some pictures coming up that Siggy did years ago for another application that we could show where we can drop in some air separators and different air vents and mixing valves that you might need on domestic. So I had to say something through this, so I dropped in some Caleffi parts. Thanks for the time.
Yeah, that's a message from our sponsor. That's right.
Right.
All right. We'll go a little bit more detail on these base components to give you an idea what it looks like. That's the prime mover. That's the system where the engine's located. The engine compartment is insulated, not just for sound, but for heat retention as well. These systems are about 49 decibels, which in the case of comparison, when I do public speaking, I usually speak at 65 decibels. I'm a loudspeaker. Other references, 49 decibels is a refrigerator or even a library. So, if this is in a high occupancy installation, say a multifamily or a hotel, there's no concern about any noise level from the engine transmitting through the building. Give you a little diagram of the heat distributor, and what I'm going to show you on the left here, where you see these braided connections. This is coming from the prime mover, the engine, where we're taking the heat off the generator, the engine, and the exhaust. There's water jackets throughout, and we're transferring that heat into this braze plate heat exchanger via this pump here. On the right-hand side, this is the connections going to the stratification tank, which has another pump and an actuator, and the control box will actually control the speed of the motors in order to optimize that heat transfer between the two systems. It begins to learn the system, it learns the hot water usage, and will work accordingly to provide maximum amount of heat for the domestic hot water. On the control panel, this is the interesting part about micro-cogeneration. The electrical connection is not complex. This is a 480 volt three-phase system. If you have a 208 building, which we've installed in 208 buildings, simply adding a transformer to the project resolves the issue. But what happens is we'll take that 480, we'll come in from the line, beyond the breaker box in the building. We'll take that 480, we'll hook it up into the contactors here, then we run it back to the power unit, the prime mover, the engine. And what will happen is that we'll take that 480 and we'll use it to spin the generator, which at this point is a motor. So we're spinning the motor to actually start the engine as a starter. Once we get to 1840 RPMs, that motor becomes an induction generator and it begins producing and flowing electricity back through the same lines, through the control system here, back into the building. So the electrical connection is very simple. The connections between components on our system are all Cat5, Cat6 cabling, so it's all plug and play. Everything's color-coded based on where it runs to. So it's a very simplified process to install. I've talked with several electricians who worked on projects for us, and they just kind of shrug their shoulders and say, hey, it's a wiring diagram, and I connect the wires. There's nothing out of the ordinary for them. Plumbing is the same thing. It's standard plumbing connections, and there's nothing unique about it as far as installation. So why thermally led? There was a question that was asked prior to during sign up, wanting to know what to do with the hot water in the summer, what to do with overnight. What do you do with this hot water when you have enough? Well, the intent is to utilize as much hot water as we can from the system in order to maximize our electrical output to, again, reduce the ROI to under 4 years. Okay, so we want to base load that heat. We want to take that 163,000 and find applications where we have a constant demand for it. Now, If we have other applications that we can use that heat for, say overnight, we put it into a brazed plate heat exchanger and do a pool. We can do snow melt, reheat, dehumidification, storage. You know, it helps improve the runtime, and this helps reduce the return on investment. So basically, the simple question is, what would I do with 163,000 BTUs? And to put that into perspective, the most popular tank type commercial water heater on the market at this time, and has been this way for a number of years, is a 100 gallon, 200,000 BTU commercial tank type water heater. We're producing 163,000 BTUs constantly, okay? So basically, you look at where you would have used a standard tank type commercial heater. Can I replace that with a cogen? The electrical and heat loading, you know, just to give you some profiles, you know, we want to base load the heat. We don't want to overproduce the power. One, nobody in the US wants to buy it back. Solar, you know, kind of did a number on the industry, and nobody wants to buy, none of the power companies want to buy power back. And if they did, in the cases that I've seen, it's like trading your car in. You know, they want to give you black book auction value, and you know, they don't want to give you retail value for it. So same thing with the power companies. They really don't want that power back. So we don't want to overproduce power, okay? But we take a look at a basic Hunter curve, in this case, an apartment building, and we can see there's a constant demand for upwards of basically almost 500,000 BTUs. In this case, though, we could take and put 2 cogens into the system and base load that heat and rely on a backup heater, a small backup heater, to get us through the peak times. This will give us the amount of power, you know, the amount of electricity we need. So in this case, you know, we don't really want to exceed the 24 kW. So maybe we just want to put the 163,000 BTUs and base load, you know, the thermally led system throughout the day. Another example would be a convention center hotel. In this case, you know, we could put in 4 systems, you know, at 650,000 BTUs and easily absorb 100 kW into a large building. Now, the interesting thing about micro-cogeneration is that it gives you some options. You can centralize and you can decentralize. And what I mean by that is, you know, we'll take for an example I like to give is a high school. You know, you have a gymnasium and showers and everything, and you have a mechanical room. And you ask yourself, you know, do I want to put all my cogens in the mechanical room, or do I want to put 2 of them out toward the gymnasium where I need the electricity and I need the hot water, and allow that to operate decentralized from the other 2 that are running the rest of the building, okay? The other examples that we've looked at some projects where, you know, it's a multi-story, multi-story complex, and every 5 floors they have their own heating system. And so we could put in, you know, a decentralized cogen for each floor, each mechanical room. Again, that's basically the example I showed you with the farm in Canada. They had a centralized mechanical room where we put the main system at. They had some outbuildings like the hog barn where they didn't want to run all the lines to, and basically, you know, use the hot water and the power decentralized locally at that particular building. So there's a lot of options as to how you can apply these systems. There's an example there of an installation we did in Rhode Island last year. The system also includes 2 Lochinvar water heaters and some storage tanks. As you can see, it's vented with category 4 stainless steel, just sealed stainless. We can vent up to 150 feet vertically. The unit itself is 29 inches wide, so it fits through all the mechanical room doors, service elevators, corridors. The compactness of it is really important for retrofits. I talked a little bit earlier about a hotel installation. We have one up in Idaho that was done several years ago when we were working through the design of the unit for the US. Basically, what they did, they put 2 units into their mechanical room, took out their heating system. They have a 400,000 BTU backup heater. And what they do, if you think about it, a hotel like this, or even your everyday Holiday Inn Express or Hilton Garden Inn with 120 rooms, you need hot water in the morning for your guests who are showering to leave. You need a lot of hot water through the middle of the day when housekeeping is doing sanitation, washing of the linens. And then you have your evening usage of hot water for your new guests that are arriving. But what do you do overnight? In this case, at the hotel in Idaho, they connected to a brazed plate heat exchanger to heat their indoor pool overnight. So they easily needed absorb the 40 kW that this system was producing, and they easily took and utilized the heat for pool heating overnight, in addition to filling up their storage tanks. Again, the backup heat was there for peak demand. So, it's just different ways to use this product. Now, looking at different installations, what I'm going to ask you to do is, here's the cogen system right here. And what I tell people all the time when I do this training is to forget what it is. Think about what it's doing. It's producing 163,000 BTUs of heat. What would I do with it? Okay. In this case, we're running it through a reverse indirect. So we have our domestic water running through the coil into the building. Again, if the sensors indicate that we have reached a point where we're running low on heat in the system for the reverse indirect, our backup heater will come on and provide that additional heat for peak demand. Very simple process. Again, if you don't get hung up on what it is, you just think about what it's doing. This could be a solar system, this could be a geothermal, this could be an electric boiler, it could be anything. In this case, it just happens to be cogeneration that is giving the facility back 24 kW during operation. Bob, you want to touch on any of the components here?
No, I think people can see where I dropped in, wherever you had a component that we can certainly help you with in that drawing. I just dropped some of the Caleffi stuff, and I think I got another schematic coming up towards the end that I can talk about a little bit more, integrating some of the things you've been talking about with the solar and the backup boilers. So you're doing great. A lot of questions. I think Eric's probably answering the questions coming in, but I think people are enjoying it. Thanks.
All right. Yeah. And again, we can do retrofit. In this case, we got a wall hung boiler heater sitting here. In some cases, you may have a system that has an old, 78, 85% efficient system. They're not ready to replace it, but they want to kind of make it last a little longer. Maybe they want to improve their efficiency. Well, we can just simply front end load the system. I mean, that's all we're doing here is just front end loading the system of an existing application with a simple connection into the loop. And bring, again, cogeneration into an old application. Another example there, I mean, you can see how compact the system is. You can see the backup heater on the right here. Again, these units are very compact. That's why they're called micro. Easily to maneuver in. It doesn't take up much room. And again, having a backup heater, we're using the cogen to charge some tanks, provide base heat, and rather than having the boiler modulate as often as it normally does without a cogen, we're just pulling it in for the peak demand. Space heating, same thing. The only difference here, we have what we call a flow master controller. And what this is, it communicates back to the control box, and what it's doing, it's monitoring the amount of heat we're getting off the cogen from the tank. It's monitoring the amount of heat that's going into the supply, and then we're monitoring what's coming back through with two sensors, because what we don't want to do is we don't want to backfeed into the loop. So what it will do, it will adjust both, it's got an actuator and a pump, and what it'll do, it'll adjust the flow rate and the pump speed to match what is needed for the system for space heating application. Again, same thing in a retrofit. We just tie into an existing system and are able to produce electricity and hot water into a hydronic loop. As I mentioned earlier, with the 6-unit job in Canada, we do have applications with multiple units. And again, this is where the centralized and decentralized story comes in at. We can put a couple of units together, or you can put single units together. The important thing, though, to remember in applications is that the cogens are hooked parallel. The storage tanks are connected in series. And the reason it's connected in series is because we need a delineated stratification point somewhere in these two tanks. If we did it parallel, what would happen? The tanks would go down evenly, and it would confuse the sensors understanding where the delineation for the stratification is. So series on the tanks and parallel on the cogens. The other option too, just to throw this out there, instead of the 2 tanks, we can also do a larger custom tank. This is what we did for the project in Canada with 6 cogens. We put in 3 large 400-gallon tanks with 8 sensors each. So there's options there to minimize footprint. I mentioned a little bit on the electrical. This is the basic schematic of the whole system. So we have our incoming power. We have our main fuses, our meter, we have our switches, our breakers. We're coming down, and then we're just going to come down into the control box. We're going to go into the power unit. And again, this power is going to go back up through here. And if we wanted to, we can hook in a reference meter to monitor the load. All that's there. And then we can distribute the load into the building. And again, all the interconnects between the components are all Cat5, Cat6 cabling. So again, it's not a complex interconnect. Bob, you want to talk about different options to use in multi-energy applications?
Yeah, thanks. So as we were talking to Tommy about doing this presentation, I happen to remember that years back that John Siegenthaler had put together some application drawings with cogen units, and in this case we're showing, I think, is yours available with a LP option too, isn't it, Tommy?
That's correct.
Yeah, so I showed it there as a natural gas or LP version of it. So just showing it with a solar thermal interface with it, and basically we used a dual coil indirect type of tank, which I know Lochinvar offers those too. And then you could, have both inputs to that tank, both energy sources input. So, to me, the buffer tank, or the tank in the middle, becomes like the transmission or the transfer case in a vehicle, where it accepts the energy from the power input, be it the cogen or the solar, and it distributes it out to the different loads in the building. The domestic water could be in the tank, and then also that could be a hydronic loop tied into it. Yeah, I'm curious about your tank. We're gonna have to talk about that a little more. That looks like a nice tank that you built with the multi-sensors and stuff. So yeah, so we've got a couple of these different application drawings that show different options, I guess. What I liked about this one here is it shows a heat pump tie in it. So think about this: if you're generating electricity, certainly you'd want to use that electricity as efficiently as possible. So instead of just putting it in the resistance load somewhere, heating loads or something like that, if you run it through the heat pump here, a geoloop heat pump, as you can see, now we got the COP advantage of whatever the system can operate under the operating conditions of that geo. So we might get a 3 or more COP. So we're using our electricity to benefit us more by using the advantage of the heat pump. And the same thing there, we've got a little solar thermal interface with that, and we're just showing some low temperature loads going out from that buffer tank or from that storage tank there. So just giving you some ideas, things to think about. One of the things, Tommy, that I thought of as you were going through here that kind of struck a chord, and I was visiting a manufacturer over in Germany years ago when we were shopping out some solar components, and actually I visited 2 different ones, and both of them had little cogens. It seems to be pretty common in some of the small manufacturing facilities over there. And I remember the one engineer saying, he said the key to make these work is, he said, you got to pull all the heat off that engine. He said a lot of them just take the cooling water temperature and use that, but he said you got to put a girdle around the generator, pull that heat off. He said you got to pull the heat out of the exhaust, you got to pull the heat out of the cooling fluid. He said you got to grab all that thermal, and like you were saying all along here, it's a thermal lead thing. So it's interesting to see that's how this unit was built, that they grab heat wherever they can off of that. So yeah, I think that's about what I had.
Okay, so just talk a little bit about the market potential. I mean, we talked about multifamily. I gave you some examples of multifamily applications. Agriculture is a big one. Pool heating, these large commercial laundries that run 24/7. These large hotels. I got a hospital on there, but it's not so much the hospital because the hospitals will use the large cogen systems. What I'm talking about here is the small outpatient surgery centers where you need some reheat because they keep the operating rooms very cold and they have to reheat in order to get a comfortable temperature for the waiting room in their offices. So, there's applications where we can do, where you can use it, for reheat. And then again, the power using up to 24 kW is very easy on a lot of these buildings. So just another example, here's another one that we did up in Rhode Island. Again, you can see the compactness of the unit. I mean, that's just wanted to show you the compactness of the unit, how everything fits in. And like I said, easy to get to. They've left adequate room to get in so we can, so they can do the oil change and a spark plug change when they're maintenance. Again, it's a very simple operation. Again, there's no major tear down of this engine like large scale cogen. So a lot of people that we've been dealing with have a lot of experience with large scale cogen, and they want to know what the maintenance cycle is. And when we go through it, we do have to reiterate, this is not an engine that you disassemble. I mean, 60, 80,000 hours, of runtime, before you even have to think about anything mechanical.
I wonder if that system, Tommy, has a backup generator too. I see there's some CAT logos on some of that electrical gear in there. Do you know if that was the case, or did that just happen to be a CAT labeled switch gear off to the left there?
I think if Eric joins it, because Eric went and did the commissioning of this unit, I think Eric might have a little bit information if he doesn't mind jumping in.
Yes, that's actually a transfer switch for a Caterpillar generator that was outside a large enough one to run the entire facility that you see in the picture on the left. And what's great is, even though the power went out, this cogen will actually synchronize with that Caterpillar generator and will cause that Caterpillar generator to slow down 24 kW, reducing load and wear on that Caterpillar backup generator.
That's interesting.
Yeah, thanks, Eric. We got some projects going at the correctional institutions in Ohio. This is the closest picture we could get to the application because it's next to impossible to get anything into a prison. So cameras were not allowed, but the installation, started off as a project. This was interesting. This started as a project with an engineering firm that they were going to put in 3 of our FTXL 400 high efficiency boilers in each of the 22 cell blocks. Ohio has a state mandate that requires public buildings to take steps to reduce their carbon emissions. And once we had the data, provided the data for the emissions on this system, the engineer changed the project to putting in one of the cogens and only 2 of the FTXL 400s. So instead of having the FTXL 400s modulating all the time, we're relying on the cogen to do the baseload heat and distribute that power consistently throughout the day. It's connected to a domestic and a hydronic system. And again, we did the first cell block, and what they'll do is they'll multiply that times 21 more to get the total amount of carbon emissions that they can report that they helped reduce. And of course, as a manufacturer, we believe in the product. I mean, we have one installed in our factory in Tennessee. We've had it installed since 2018. We've done several maintenance cycles on it. It runs winter, summer. We're using it for either domestic hot water or hydronic. We have all the capability in our mechanical room. And of course, as you would expect, all the boiler equipment is Lochinvar equipment in our mechanical room. But we use it to test units and to get some runtime on units and some life cycles and things like that. So if you've been on the tour at Lochinvar, one of the things that we do take you now, we'll take you back to see the system and let you see it and understand just how quiet it is. We're hoping to start up towards later in the fall once this COVID-19 clears up. And yeah, I did want to get that plug in for COVID-19 because I think 20 years from now, when young engineers are graduating college, they'll hear that and they'll have to ask what was COVID-19. So I wanted to get that somewhere in the presentation, Bob.
The 19 will be key.
So just some quick resources. U.S. Department of Energy has an e-catalog for combined heat and power. Excellent resource. If you forget the address, just Google DOE CHP e-catalog. It has all the manufacturers, large and small, every model, every unit's available. People have listed. It's a clearinghouse where manufacturers, specifiers, installers, engineers, designers, it's kind of a meeting place to have all the resources available. All the calculations, everything is done on an equal footing. So when you look at product, when you look at efficiencies and power outputs and heat outputs and so forth, it is all apples and apples comparisons. We're all using the same DOE calculations to provide them with information. So you get a very good unbiased look at different products out there on the market. The CHP Technical Assistance Partnership, this is another run by the Department of Energy. There's a number of regions around the country. They're staffed with a lot of university PhDs that will gladly work with you to develop an installation project. If there's something you want to try, something you want to get installed, they're an excellent resource. They're there to help. We've been utilizing them for at least past year and a half since we launched this product. Eric is in the process of doing multiple webinars with them to get them more familiar with the technical aspects of our product. But another good resource locally in your region, and again, they're there to help. They're willing to help. They look forward to helping because it all brings a learning experience to them, and they can actually translate some of that to their student body as they work on these projects. Energy Solutions Center, another good resource, has information on cogen systems. And Lochinvar, Eric Morrow, he's on the call today. He's our product application manager. Eric is experienced with large-scale cogen and micro-cogen, is a master electrician licensed in numerous states throughout the country, and is our electrical go-to guy. So we do have the resources in place to talk both the hydronic, domestic, and electrical aspects of this product. So with that, if there are any outstanding questions that Eric might have not answered, or if there are any questions that Eric you came across that you think might be worth bringing public, we can do that as well.
I've been having fun trying my best to answer all the questions, and I apologize if I missed anybody. The way it stacks them is a little difficult to keep up, but I've been trying my best. Just to let everybody know, Lochinvar.com, you can get a hold of us. If anybody wants my personal information, Tommy, you can share it or how y'all want to do it here, but we're here to help everybody understand the technology and appreciate your time for letting us do this.
Yeah, Eric, were there any popular questions, any themes in particular that you came across?
We had people all the way from Quebec, Canada, several people from Canada. We had a few on a little bit, but the most biggest thing I have in question is just want to know what we can do with the heat. They heard domestic hot water, and that I guess a few got hung on that, and they're just wondering, can they use that heat for other applications?
Yeah, and that's what I think I mentioned that throughout the presentation. That's the key to optimizing the system, is to have use for that heat. Again, hotel, you have the ability up north for snow melt, or you can use it for pool heating. The way the Finger Lakes Community College innovatively used it to just circulate overnight to put a base heat, just a mild heat throughout their building. That's key to it. You can storage, if you want to put it in storage tanks, you can do that. But again, you know, it's 163,000 BTUs. It's light heat, but again, you know, there are all kinds of places. If you look long enough, you know, and you research a project, you know, there are places to put that heat. You know, you can run through fan coils if you need it to do that. So there's just different applications.
Well, I'll say that Nathan White up in Alaska raised his hand. If you need an application up there in that part of the country, he'd be glad to help you with that. I think you know him as one of your EIP contractors, so nice to have him on board today. Hi, Nathan. Yeah, I don't know which questions that you might answer as we went through there, Eric. A couple of them, there's a common theme. Obviously, price comes up quite a bit. I don't know how you guys want to handle that, but there's another one here I thought was interesting. Oh, your maximum water temperature you can supply, is it close to what the cooling temperature would be on an engine, or?
Well, yeah, it's basically, you know, I mean, the engine's producing, you know, heat at about 220 degrees like your car. Once we transfer it into the stratification tank, we can produce 180 degree hot water.
Okay, so if you had a high temperature application like at a commercial facility or something like that, you can get to that temperature.
Mm-hmm.
Let's see if I can pick another one or two here because we've got a few minutes, it looks like.
Our big one to also know is our max return temperature is 165 degrees Fahrenheit.
Yeah, so yeah, and that kind of puts it in relative terms when we talk about needing cooling, you know, cooling temperature to maintain the engine temperature. It's relative, yes. So 165 degree water, you know, that's relative in terms of coolness when we're talking about, you know, going back to recirculate with the engine, you know.
Yeah, I mean, there's certainly a lot of questions about, you know, the cost of operating. It's going to vary based on the cost of your fuel source, right? I mean, I know there's some places where the peak electric rates go up and down based on the generation that they have when they have excess capacity, and obviously the natural gas prices, somebody noted, can go up quite a bit in the wintertime in certain areas. Right now, here I'm in Missouri with LP prices under $1 a gallon. I wish I could run my truck on LP right now. So, you know, that, you know, you've got to know what your fuel prices are locally and how much they vary to obviously put that in the form. Somebody asked if you have a spreadsheet or something for doing some ROI calculations.
We do. We're actually working on a modified version with this easy user interface that we'll eventually put on our website. But right now we're working these cases individually because you know, the experience level that we're finding with micro CHP, you know, sometimes we really want to be involved with these to ensure that it's a success. You know, we don't want you know, anything to go wrong to put a bad taste in the industry that, you know, that about the technology. We want to make sure that the applications that we do, we fully vet and ensure that it's plumbed properly, it can consume the load, we have something to do with the power and so forth. So yeah, we work closely with our customers to address everything.
Yeah, I don't see this ever being an off-the-shelf product. It's going to have to be specific to the application in every case, and that's why it's good to have you guys. I know you have a nice toolbox on your website with other calculators and simulators and stuff like that. So maybe that's where you could house some of the information on this as you build those different calculators or simulators, whatever you come up with. So what else have we got here? I'm trying to pick a couple that seem to be pretty interesting. Anything else jumped out at you, Eric? I know some of the electrical ones you could probably answer better than I, as far as wiring and voltage and stuff like that. I think you probably grasp. Yeah, I know what you mean. They come in pretty fast here in that little box. It's hard to keep up with the questions. But you know, if there are any that we didn't answer, obviously the Lochinvar folks will certainly email them back to you, and we'll you know, have the presentation available, like I say, if you want to review some of those slides. But you know, it's limited, I think, Tommy, by your imagination as far as what you can do with when you start putting tanks in and moving that energy around it. You know, as long as you have a place that you can use the thermal side of it, it seems like it's got some good potential out there.
And Bob, you're right. I mean, that's the whole thing. That's why I reiterated several times. You know, don't focus on so much of what it is. Focus on what you would do with 163,000 BTUs. You know, or more if you want to put multiple units together. You know, if you focus on the heat, the applications are there. I mean, it's just like size in a boiler.
Yeah. Yeah, I would think manufacturing. I know we've got a big Kraft Foods facility here that actually make macaroni and cheese here in Springfield, Missouri, one of the most profitable products for Kraft Foods, and that line has to go 24/7. So there's a lot of thermal load, and if that line goes down, it's a big expense for them. So an application like that where you've got a 24/7 load would be ideal. It just never goes away, the need for the the heat and energy in a plant like that. So.
Well, Bob, I can't disclose the location, but I can tell you the carb test unit that we're going out to do our catalytic converter life cycle test is a manufacturer, a food manufacturer that runs 24/7.
Yeah.
That's how we'll maximize our runtime. So we will have an application in food processing that we'll be able to refer to once we complete that test cycle.
Nice. An interesting application, I thought, thinking of Nathan up there in Alaska, we did a big solar thermal array on a school up there, and they took that whole solar thermal array and they just dumped it in the ground to warm the ground for their heat pump for their wintertime load on that building. So they didn't even make domestic water because they said, we're going to load that bank in the ground up through the summer months when nobody's in school, and then we'll have that ground temperature up a little bit so our COP on our heat pumps when they get into the heating mode. So there's another example of what you could do if you had to dump some of that thermal load is if you had a loop field, you could start bringing it up to temperature for your winter heating load. So looking forward to seeing everybody again. Thanks to my team. Thanks to Lochinvar. Thanks to the attendees. Have a good day.